Okay, let's look at this following problem. How many ways can you arrange the 13 hearts in a deck of cards so that the face cards are all next to each other? So we just take the 13 hearts of the deck. So the ace of hearts, the 2, the 3, the 4, the 5, the 6, 7, 8, 9, 10, jack, queen, and king. How many arrangements are there where the 3 face cards, the jack, queen, and king, are all together? This is kind of a tough one. So I'd say the best way to approach this is think about what you would physically do to make an arrangement where this is true. Think about the steps you would take, and that will help you to determine how to count this. So maybe pause the video and think about the physical steps you would take to arrange this. Okay, so what I would do for this one, if I was to physically do this, I would take the 3 face cards together and arrange them. So first thing I would do, I would take these 3 cards here, and I would arrange them in some order. So that'd be the first thing. And the second thing I do in some sense is I'd put an elastic band around these because I don't want to separate them anymore. So I would keep keep face cards together. As one unit. And then, once I do that, I would arrange the other non-face cards with the face unit, we'll say, from part 2. So, for example, let's say, I'll do step 1 here, just as a little example. So let's say I wanted the order queen, or I'll do it like this, actually. Queen, jack, king. So I arrange those, and I'm going to put an elastic band around them. So I'm going to treat them as one object. Now, how many objects do I have left? I have 10 other objects, so I can put them wherever. So let's have maybe let's say a 2, 5, 3, 7. Then I'll have the queen, jack, king, and then I'll have the other 6. So maybe like the 10, and then the ace, and then the 4, and then the 9, and then the 8, and then what am I missing? The 6. So there's one arrangement. And if we think about what I just did there, I'm doing kind of 2 separate arrangement problems. So I'm arranging the 3 face cards first, and then I'm arranging these non-face cards with this unit. So there's 10 cards plus that 1 unit, 11 things to arrange. So what I'm doing is I'm arranging my 3 face cards, and I'm arranging the non-face with that 1 unit where I bundled those 3 face cards together. So let's count this up. I'll just scroll up here. So how many ways are there of arranging our 3 face cards? Well, there are 3 factorial. There's no repeating symbols or anything, so it's just 3 factorial since we have 3 cards. And then, once I do that, I'm arranging the 10 non-face cards with that 1 face card unit, so I have 11 things I'm arranging. And again, there's no repeats. They're all distinct. So I'm arranging 11 things. And if you were to work this out, 239,500,800. But for most purposes, unless for whatever reason you would need to calculate this number, this is a fine answer. You could just leave it like that. But it is quite a few. It's actually pretty nuts to think just with those 13 cards and that small condition where just the face cards stick together, there are over 200 million different arrangements. And here's something that's quite mind-blowing. I'm sure a lot of you have shuffled a deck of cards before, and there are 52 cards in a deck, and every time you shuffle, you get an arrangement of those 52 cards. So you could ask, how many different arrangements of cards are there? There's 52 factorial. And how big is that? Well, that is roughly, and I'll say roughly because this number is absolutely huge, something like 8 times 10 to the 67, which is 8 followed by 67 zeros. That is a wild number. And that's pretty wild. How many people exist in the world right now? There's something like 7.5 billion. That's 7.5 times 10 to the 9. So that's how many people there are. And if you think about it, there are way more arrangements, different arrangements of cards than people. How much more wild does it get? And just to give you another kind of foothold of how big these numbers are, the amount of water on the Earth in liters is something around the lines of, well, around 1 times 10 to the 21 liters of water in the world, 1 followed by 21 zeros. So these sizes are ginormous. What about atoms in the universe? There are about 1 times 10 to the 80 atoms in the universe. Think what an atom is, and think about how big the universe is. And that's how many atoms exist in it. And this is how many different ways you can shuffle a deck of cards. And if you think about it, the chances that if you give a deck of cards a good shuffle, the chances that nobody has ever shuffled that combination of cards the way that you have them in your hand there is extraordinarily close to 100%. It is basically 100%. Every time you give a deck of cards a really good shuffle, the chance that you're holding a unique order of these cards is almost certain, as close to certain as you can reasonably get, which is wild to think. Let's try this one. How many 6-letter words are there? And by words, all I mean is any string of 6 letters put together. It doesn't have to be an English word. It doesn't have to make sense. Anything at all works. That's what I mean by a word. So how many 6-letter words are there so that all of the letters are in alphabetical order? So something like this would be fine. So D, G, H, M, S, V. There is an example of a word that has 6 letters where all of the letters are in alphabetical order. How many of those are there? Now, there's a clever way of approaching this, which makes the problem very easy, and a non-clever way, which makes it almost incalculable. It would take you so long to do it. So, I will tell you the way to avoid. The way to avoid is breaking this down by cases, saying, well, what if the first letter was A? Well, if the first letter is A, then there are 25 choices for the next letter. It could be B, C, D, E, F, G, all the way to Z. But the choice that I make there, let's say I choose B. If I choose B, then there's 24 for that, for the subsequent one. But if I choose something like E, well, E is the fifth letter, so there are only 21 choices for the one after that. Or maybe I chose J, which means there's only 16 choices for the next one. So you can imagine that this problem is going to grow out of control if you do it like this. It is possible, but it would take you a long, long time to approach it like this. So I don't suggest that. Maybe pause the video and think about how you could do this. And a good way, I would say, is think about how you would physically come up with one of these words. If you had a tile with each letter on it in a bag, something like Scrabble, if you know what Scrabble is, how would you make a 6-letter word so that the letters are in alphabetical order? Okay, so what I would do if you think about it, let me write down a few of the letters of the alphabet. I want to write down them all, but just for the interest of time and space, I'm just going to write down the first few and the last few, and I'll just let the other ones just be encapsulated in those dots there. But I want that to represent the whole alphabet. Well, if I was to make a word with 6 letters in alphabetical order, what I could do is I could just pick the letters first and then put them into alphabetical order. So kind of my steps, if I were to do this physically, I would pick 6 letters and then put in alphabetical order. And if you think about it, the order in which the letters are picked above isn't going to make a difference because I'm going to put them in alphabetical order anyway. So really, there's only 2 states for this problem. There's 26 letters in total. 6 are going to be picked, and 20 are going to be not picked. So you could imagine picks being represented by a check mark and not picked represented by an X. So any arrangement of 20 X's and 6 check marks give me what letters to pick. For example, maybe I didn't want to pick A, I did want to pick B, C, not D, I did want to pick E, not F, not G. So what is that? That is 3 picked, and let's pick X, Y, and Z, and all of the other ones I did not pick. So that gives me one arrangement. It gives me B, C, E, X, Y, Z. All the other ones aren't picked. So you can imagine any order of these 20 X's and 6 check marks gives me a different 6 letters for my word. And I know how many there are here. So there's going to be 26 factorial, since there are 26 letters, 6 repeat check marks, 20 repeat X's. So that's how many ways I can pick 6 letters out of 26. And how many ways can I put them in alphabetical order? Well, if you have 6 letters, there is only one way to put them in alphabetical order. So, in fact, you don't need to do anything. Just picking the letters just gives you the alphabetical order. So for this one, there's 26 factorial over 6 factorial, 26 factorial, which I'll write as 26 times 25 times 24 times 23 times, this should be a 20 factorial, times 22 times 21 times 20 factorial. That's all the numbers 20, 19, 18, all the way down to 1 multiplied together. Over, I'm going to write this one out, 6 times 5 times 4 times 3 times 2 times 1. And I'm going to write this as 20 factorial because I want that to cancel. So that cancels. And let me factor out all of these denominator terms. So let's factor out a 6 out of the 24. 6 times 4 is 24. Let's factor a 5 out of the 25. 5 times 5 is 25. Let's factor a 4 out of this guy. We have a 4 there, so we might as well just factor that out. We'll factor a 3 out of, where can the 3 come out of? The 21. So 3 times 7 is 21. And let's factor a 2 out of, I guess it doesn't matter. Let's factor it out of the 22, make that 11. So I just have to multiply 26 times 5 times 23 times 11 times 7. And that'll give me the number of different 6-letter words where the letters are in alphabetical order. And if you do that, you will find that you get, let me write it in here, 230,230 different 6-letter words where the letters don't repeat and they're in alphabetical order. All right, let's look at this one final problem. So we have a gym class, there's 21 students, and the gym teacher wants to play 4 different games at the same time. A 10-player basketball game, a 4-player double badminton game, a 5-player street hockey game, and 2-player tennis. So, and inside of each game, things will change a whole bunch. So you're considering once they're playing a certain game, you're not considering different positions or anything like that. So the question is, how many ways can the teacher arrange the students into these games? So pause the video now and see if you can solve this problem. Think about how many students there are, how many different states that these students can be in, and then from there, see if you can solve the problem. Okay, so we know that there are 21 students, so 21 objects in total. We know 10 students are going to play basketball. Maybe we'll use the letter B to represent that. There's going to be 4 playing badminton. We already used B, so let's use I don't know. M for badminton. 5 will play street hockey. So we'll use H for that. And 2 will play tennis. And we'll use T for that. And let's make sure we covered all states of these 21 students. 10 plus 4 is 14, plus 5 is 19, plus 2 is 21. So each student will have a state of either B, M, H, or T. And as long as you number the students from 1 to 21, any arrangement of these 10 Bs, 4 Ms, 5 Hs, and 2 Ts will give you a new arrangement of students playing each sport. So we just need to count the arrangements of these 21 letters where 10 are Bs, 4 are Ms, 5 are Hs, and 2 are Ts. And we know how to do that. That is 21 factorial, since there are 21 letters in total, over 10 factorial, 4 factorial, 5 factorial, times 2 factorial. And then it's just a matter of simplification. You can leave this as an exercise, but something this complicated, I would just probably accept this answer here. It shows that you know how to do these problems, and the rest is just a matter of calculation. But if I asked you to calculate it, I'll just write down the answer, and you can check it if you want to practice kind of canceling factorials and doing multiplication. You would get 2 billion 444,880. So that is a lot of different arrangements of just these 21 students into 4 different games. Arrangements grow quite quickly as the number of symbols grow. That's something to keep in mind. So something like 21 factorial, that's a huge number. 21 factorial is somewhere around 5 times 10 to the 19. So a 5 followed by 19 zeros. That's quite huge. So thinking about that, arrangements can grow quite quickly, which is very interesting. I will say the following, and maybe I'll do another slide on it. The best way to get good at these arrangement and counting problems is just to keep on practicing. The more you do it, the better you will get at kind of interpreting how to write these problems in terms of either or together, the multiplicative property, the additive property, and arrangements. So you will for sure see a bunch of examples posted that will allow you to practice these. And some of them will be quite easy, some of them will be quite difficult. So I think it's absolutely worth it to keep practicing these. A lot of them you have to think about in the correct way in order for them to work out nicely. So if you do get stuck, feel free to reach out to me and give me an email, and we can chat about the best way for you to approach it. So I will say, again, just keep practicing these. They are a little bit difficult sometimes. And every problem, for the most part, is a little bit different. So you just have to get good at figuring out the best way of approaching each one.